Imagine yourself on a sun-drenched beach in ancient Greece, more than 2,000 years ago. You pick up a seashell. You break it in half. You break that half in half again. The question arises, can you keep doing this forever? A philosopher named Democritus thought about this. He didn't have laboratories or particle accelerators. He had only the power of his own mind, his reason. He proposed that if you kept cutting matter, you'd reach a piece that could not be cut any further. He called this final indivisible particle atomos, the Greek word for uncuttable. It was a staggering leap of the imagination, a profound attempt to understand the nature of reality. Democritus believed everything in the cosmos, the stars in the sky, the water in the sea, you and me, was made of tiny, indestructible atoms moving through an empty void. Different substances were made of different kinds of atoms, with unique shapes and sizes. A piece of iron was strong because its atoms were jagged and hooked together. Of course, not everyone agreed. More influential philosophers like Aristotle dismissed atoms entirely. He believed all matter was composed of 4 elements: earth, air, fire, water. Because Aristotle's influence was immense, the atom idea was largely forgotten. It faded into the background, a footnote buried for nearly 2 millennia. The dream of Democritus did not die. It merely slept. It was a seed of an idea planted in the soil of human curiosity, waiting for the right conditions to sprout. It would take 2,000 years for science to develop the tools and mindset to test this thought experiment. The journey would require moving beyond pure reason to measurement, observation, and repeatable experiments. The stage was set for a scientific revolution that would vindicate Democritus and reveal a universe far stranger and more wonderful than he ever dreamed. Fast forward to the early 1800s. The world is lit by gas lamps, steam engines and factories puffing smoke, steel mills and ironworks. In England, a humble Quaker schoolteacher named John Dalton was obsessed with the weather. Dalton studying gases in jars, meticulous measurements and notes. He noticed something fascinating. Gases always seem to combine in simple whole number ratios. For instance, water was always made of the same proportions of hydrogen and oxygen. This wasn't random. It was a rule. Dalton resurrected the ancient idea of the atom to explain this order. He proposed that all matter was made of tiny, indivisible particles called atoms. Dalton's atomic theory was a game changer because it was built on evidence. He wasn't just thinking, he was measuring. He proposed several key ideas. First, all elements are made of atoms. Second, atoms of a specific element are identical but differ from other elements. Third, atoms cannot be created or destroyed. And finally, chemical reactions are simply rearrangements of atoms. To visualize his atom, think of a tiny, solid, featureless sphere, like a microscopic billiard ball. It was simple, elegant, and it worked. It explained the laws of chemistry that were being discovered at the time. This model was revolutionary. It transformed chemistry from mysterious recipes into a quantitative science. For the first time, scientists had a framework to understand why chemicals reacted in predictable ways. They could visualize elements as distinct families of these tiny billiard balls, each with its own unique weight and properties. Dalton's work provided the first scientific definition of an element. An element, a substance made of only one type of atom. A compound, 2 or more types of atoms chemically bonded together. Dalton's atom was the starting point of modern chemistry, but it was still just a solid, unbreakable sphere. It had no internal parts. As the 19th century drew to a close, physicists were exploring a new frontier: electricity. They were using devices called cathode ray tubes, glass tubes with most of the air pumped out. When a high voltage was applied across the tube, a mysterious beam would shoot from the negative terminal, the cathode, to the positive terminal, the anode. These cathode rays were invisible, but they caused the glass at the far end of the tube to glow. What were they? Were they a form of light, like an ethereal wave, or were they a stream of tiny, fast-moving particles? The scientific community was divided. A British physicist named J.J. Thomson decided to solve this mystery in 1897. He was a master of experimentation, and he subjected these cathode rays to a series of clever tests. He used magnets and electric fields to see how the beam would bend. He observed that the ray was deflected away from a negative plate and toward a positive one. This was the smoking gun. Light has no charge and would not be affected in this way. Thomson had proven that cathode rays were not waves. They were a stream of negatively charged particles. But Thomson did something even more astonishing. By measuring how much the beam bent, he was able to calculate the mass-to-charge ratio of these particles. He discovered that these particles were incredibly tiny, almost 2,000 times lighter than hydrogen. This was a shocking revelation. The atom, the uncuttable billiard ball of John Dalton, was not indivisible after all. It had smaller pieces inside it. Thomson had discovered the first subatomic particle, the electron. For this monumental discovery, he would win the Nobel Prize in Physics. Thomson needed a new model to include his newfound electron. He proposed what became known as the plum pudding model. Imagine a sphere of positively charged pudding with negatively charged electrons scattered throughout, like raisins in a cake. The atom as a whole was electrically neutral, with the negative charges of the electrons perfectly balancing the diffuse positive charge of the pudding. It was a sensible model that accounted for the electron and the atom's neutrality. J.J. Thomson's plum pudding model was the accepted picture of the atom, but one of his former students, a brilliant New Zealander named Ernest Rutherford, decided to put it to the test. Around 1909, Rutherford designed an experiment that was elegant in its simplicity and, honestly, staggering in its results. He would fire these tiny, positively charged particles, called alpha particles, at an extremely thin sheet of gold foil. Gold was chosen because it could be hammered into a sheet just a few thousand atoms thick. According to the plum pudding model, the positive charge in the gold atoms was spread out, kind of like a thin fog. The fast-moving alpha particles should therefore pass straight through the foil, with only minor deflections. Working with his assistants, Hans Geiger and Ernest Marsden, Rutherford set up the experiment. They placed a detector screen all around the gold foil to see where the alpha particles would land after passing through. As expected, most of the particles flew straight through the foil, just as the plum pudding model predicted. They diligently recorded the results, counting the tiny flashes of light on the screen. But then, they observed something completely unexpected. About 1 in 8,000 alpha particles didn't go through. Instead, it bounced back, as if it had hit something solid and massive. Rutherford would later describe his astonishment, saying, "It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you." This single bizarre result just couldn't be explained by the plum pudding model. A diffuse pudding of positive charge could never repel an alpha particle with enough force to send it ricocheting backward. Rutherford puzzled over this for months. He eventually realized that the only way this could happen was if the atom's positive charge, and most of its mass, was not spread out at all. Instead, it must be concentrated in an incredibly small, dense, positively charged core at the center of the atom. He called this core the nucleus. Based on this insight, Rutherford proposed a new model of the atom in 1911. It was a revolutionary departure from everything that had come before. In his nuclear model, the atom was mostly empty space. At its heart was the tiny, heavy, positive nucleus. Rutherford's nuclear model was a brilliant success in explaining the gold foil experiment, but it had a fatal flaw, a ghost in the machine from the world of classical physics. According to the laws of electricity and magnetism known at the time, an orbiting electron is an accelerating charge. An accelerating charge should continuously radiate energy, lose speed, and spiral inward, crashing into the nucleus in a fraction of a second. If this were true, every atom in the universe should have collapsed long ago. Clearly, atoms are stable. The universe exists. Rutherford's model was beautiful, but it was fundamentally unstable. Something was missing from the picture. The solution came from a young Danish physicist named Niels Bohr, who had worked with Rutherford. Bohr was fascinated by a new and strange set of ideas called quantum theory, which proposed that energy was not continuous, but came in discrete packets or quanta. He boldly applied these quantum ideas to the atom in 1913. Bohr suggested that electrons could not orbit the nucleus just anywhere. Instead, They were restricted to specific fixed orbits, like trains running on designated tracks. Each orbit corresponded to a specific energy level. As long as an electron stayed in its designated orbit, it would not radiate energy, and it would not spiral into the nucleus. This was a radical departure from classical physics. It was like saying you could only walk on certain steps of a staircase, but never in between them. In Bohr's model, an electron could jump from a higher energy orbit to a lower one. When it did so, it would release the extra energy not as a continuous stream, but as a single packet of light, a photon, with a very specific wavelength or color. This explained another long-standing mystery: why elements, when heated, emit light only at specific, characteristic colors. These colors were the spectral fingerprints of the elements, and Bohr's model finally explained why they existed. Bohr's model was a strange hybrid, a mix of classical planetary motion and new quantum rules, but it worked remarkably well for the simplest atom, hydrogen. The discovery of the neutron completed the basic picture of the atom that we still use today, but getting there required solving another puzzle hidden in the nucleus. Scientists could measure the mass and the charge of an atom's nucleus. They knew the nucleus contained positively charged protons, which accounted for the positive charge. But when they added up the mass of the protons, it was always less than the total mass of the nucleus. For example, a helium nucleus had the charge of 2 protons but the mass of about 4 protons. There was missing mass. Where was it coming from? Rutherford himself theorized that the nucleus might contain a neutral particle, formed by a proton and an electron bound tightly together. This hypothetical particle would have mass but no electric charge, making it incredibly difficult to detect. It wouldn't be deflected by electric or magnetic fields, and it would pass through most matter like a ghost. For over a decade, the search for this elusive neutral particle was on. Laboratories around the world tried to find evidence of its existence, but the particle's lack of charge made it a phantom in their experiments, leaving no tracks. The breakthrough finally came in 1932, thanks to the English physicist James Chadwick, another of Rutherford's brilliant students. Chadwick was studying a strange new radiation that was produced when the element beryllium was bombarded with alpha particles. This radiation was uncharged, but had enough energy to knock protons out of paraffin wax. Chadwick meticulously measured the energy of these ejected protons. Through a series of brilliant calculations, he proved that the mysterious radiation could not be a form of light, like gamma rays. Instead, it had to be a stream of neutral particles, each with a mass almost identical to that of a proton. He had found Rutherford's missing particle. He called it the neutron. The discovery of the neutron completed the basic picture of the atom that we still use today. The atom consists of a tiny, dense nucleus containing positively charged protons and neutral neutrons. Surrounding this nucleus is a cloud of negatively charged electrons. The number of protons determines the element, its chemical identity.